Hello, everyone. Today, I'm going to introduce a rather interesting innovation in language models, Byte Latent Transformer, BLT. This is a research work released in December 2024 by institutions such as Meta and the University of Washington. Before introducing BLT, let's first understand a fundamental issue that exists in current large language models, tokenization. What is tokenization? Simply put, it's the process of splitting a piece of text into smaller units. For example, the sentence, "I like artificial intelligence," might be split into parts like "I like artificial intelligence." Existing large language models, such as GPT, Llama, etc., all require such tokenization processing first before they can understand and generate text. However, this segmentation-based approach has the following main issues. 1. The issue of language bias. Like a translator who is proficient in English but not so familiar with Chinese, existing segmentation methods often handle English very well, but they are less friendly to Chinese, Arabic, and other languages. This is because these models are primarily trained in English. 2. Poor anti-interference capability. If the input text contains minor errors, such as spelling mistakes, the model may completely fail to understand. This is like when humans can still understand apple, even if it is written as apple, but the machine might get confused. 3. Lack of character form understanding. The model does not understand the internal structure of characters. For example, when seeing cat and cats, it does not know that they are actually the singular and plural forms of the same word. 4. Limited scalability. The model only recognizes content from a predefined vocabulary, like a student who only knows 2,000 Chinese characters, and is helpless when encountering rare characters. Thus, BLT proposed a new architecture that directly processes text data at the byte level. It mainly includes three innovations. 1. Dynamic byte patching. BLT adopts an intelligent approach to handle text. It dynamically adjusts the processing method based on the complexity of the text. 1. First, a small predictor is used to determine the difficulty at each position, that if the next character is easy to guess, for example. After China, it is highly likely to be people. The difficulty value, entropy, at this position is low. If the next character is hard to predict, for example, at the beginning of a sentence, the difficulty value at this position is high point 2. When encountering a high difficulty position, BLT will initiate a new processing unit, patch, allocating more computational resources to this portion of the content. This design is highly efficient. For simple content, such as repeated words, it uses larger patches to process more content at once. For complex content, such as sentence beginnings or proper nouns, it uses smaller patches to carefully process each part. This is similar to how, when reading an article, we might quickly skim through the simple parts and slow down to carefully read the more difficult sections. 2. Three-layer architecture design. BLT adopts an elegant three-layer design, including a lightweight local encoder that encodes the input byte sequence into patch representations, a main global latent transformer that processes at the patch level, and a lightweight local decoder that decodes patch representations back into byte sequences. This design maintains access to the original byte data while enabling efficient large-scale computations. 3. Flexible computation allocation. By dynamically adjusting the patch size, BLT can use larger patches for simple, predictable text segments, reducing computational load. Use smaller patches for complex, uncertain text segments, increasing computational precision. Extend model scale by increasing patch size under a fixed inference budget. Next, let's take a look at the experimental results. The results show that BLT has achieved satisfactory outcomes in multiple aspects. In terms of performance, BLT has for the first time achieved byte-level model performance comparable to token-based Llama 3. With the condition of 8B parameters and 4T bytes of training data, BLT has successfully reached a level comparable to current mainstream tokenization models. More notably, BLT demonstrates a clear advantage in computational efficiency. While maintaining the same performance, its inference computation can be reduced by up to 50%. By flexibly adjusting the patch size, BLT can further expand the model scale under the constraint of a fixed computational budget. Moreover, BLT also performs excellently in terms of robustness. Compared to traditional models, it exhibits stronger resistance to input noise, performs more prominently in character-level tasks, and also achieves significant performance improvements when handling low-resource languages. These advantages fully demonstrate the advanced nature and practical value of the BLT architecture. The significance of BLT lies not only in performance improvement, but also in pioneering a new technical direction that IT breaks free from the limitations of traditional word segmentation, bringing new possibilities to language model architectures and providing a fairer, more universal paradigm for multilingual processing. Furthermore, BLT offers new ideas for optimizing the efficiency of large models, and its open source code has been released on GitHub, which will help advance related research. However, there is still room for improvement in BLT. First, the current model size is limited to 8B parameters, and further validation is needed for its effectiveness on a larger scale. Second, the training efficiency of the model still has room for optimization. Finally, the practical application effectiveness of BLT in specific domains requires further verification. In summary, BLT represents an important innovative direction in language model architecture. Through ingenious dynamic byte grouping and a three-layer architecture design, it achieves for the first time the performance alignment of byte-level models with mainstream tokenization models, while bringing significant improvements in efficiency and robustness. This work provides new insights for the future development of language models, and it deserves our continued attention. All right, that's it for today's introduction. If you're interested in BLT, you can check out the original paper or visit its GitHub repository for more details. Don't forget to like and subscribe, and we'll see you in the next episode.